Hi, everyone. My name is Sterling Mitchell. I was a Master's of Applied Science student under Professor Dean Hutchison. I'm currently working for BGC Engineering, and I'm here to present some of my thesis work that I completed in the fall of 2021. So the work was entitled An Assessment of Rockfall Triggers and Seasonal Weather Trends Through Examination of Railway Slope Management Procedures. So I'll quickly outline what this talk is going to cover. First, I'll discuss the motivation for this work and some background on the topic. Then I'll give an overview of the two sites selected for analysis and present some data from their respective rockfall and weather records. I'll also discuss the analysis methodology, present the results, and have a brief discussion on the methods. And finally, I'll point out the key conclusions and some potential future work. So as many of you already know, rail transportation is an integral part of the Canadian supply chain. In 2018, Canadian Railways employed over 32,000 people across the country and were responsible for 70% of all intercity freight and 50% of all exports. To accomplish this feat, rail networks cross remote and rugged terrain with a variety of geological and climatic conditions, exposing to various geohazards, including rockfalls. Rockfalls on or near the railway can cause operational delays, damage, train derailments, injuries, or even fatalities. The maintenance and management of slopes along railways is challenging, and the railways industry is continuously looking to improve their understanding of hazards so they can make proactive rather than reactive decisions. My research looks at rockfall triggering mechanisms by assessing rockfall and weather records in an effort to support hazard mitigation. This was done by examining two railway subsections, Heron Bay, operated by Canadian Pacific Rail, and Gagnon Sud, operated by the Quebec North Shore and Labrador Railway, QNSNL. Both sites conduct extensive rockfall and geohazard monitoring and keep records of the date, location, and relative size of previous events. By evaluating these rockfall and weather records, the goal is to better understand how weather conditions influence these rockfalls. Many academics have studied this topic, and previous results have shown that the two primary weather-related rockfall triggers are freeze-thaw cycling, which is the process of ice formation and melting at the surface of the rock mass, causing erosion, and precipitation, mostly in the form of rainfall. For this reason, these two weather conditions will be the focus of my analysis. Now, there are various ways that the railway can conduct hazard mitigation. One is to look at managing the source by stabilizing or removing the hazard entirely to reduce the chance of occurrence. A second option is to manage the deposition of the hazard by using rock fences or rockfall mesh to reduce the possibility of reaching the track. A third option is to implement operational measures that reduce the likelihood of encountering a rockfall unexpectedly, which is what this work focuses on. Even more precisely, we're going to focus on understanding the temporal hazard, attempting to answer when are rockfalls most likely to occur so they can be avoided in the future. And we can really only use this method because of the investment CP Rail and QNSNL have made into understanding rockfalls along their sites, usually again from applying the other two methods. So starting with the Heron Bay or HEBA subsection, the track runs east-west along the north shore of Lake Superior. The area of track selected for in-depth analysis is a total of 3.4 kilometers in length and contains the Red Sucker and Mink tunnels. Rockfall activity is relatively common along the stretch of track, and the area is of particular interest to CP Rail, as derailed trains are likely to go into Lake Superior. This section of track is located within the Coldwell Alkali Complex, a plutonic body comprised mainly of syenite with smaller gabbroic intrusions. Regional strike-slip faulting results in northeast compression of the track area and the formation of local faults that run nearly perpendicular to the track. Slope distance in the area can range from being adjacent to the track, shown in image A, to being over 100 meters from the track, as shown in image B. The rock cuts have a blocky to massive nature, as shown in photo C, with planar to undulating joints. The track was first established in the 1890s, and in the 1960s, the Coldwell tripwire slide fence was installed. The design was for this fence to alert CP when a rockfall event had occurred and broken the tripwires, potentially leaving dangerous rockfall debris along the track. Following a derailment along CP track in 1974, the Transportation Board of Canada required that CP conduct an evaluation of all rock cuts along the track network and develop a priority stabilization schedule. This would lead to the development of a systematic slope rating system, which CP implemented across its network. In 1995, CP would build on the initial 1974 system and implement a new directive that put an increased focus on the timing of potential rockfalls, changing the slope ratings from letter grades to urgent, priority, observe, and okay. Both systems required the expert judgment of senior geotechnical engineers to determine the rating of a given slope segment, making them expert-based systems. This allows for more flexibility, giving inspectors the opportunity to develop a custom interpretation of the slope, but also means that the decision-making process is not documented in a consistent fashion and can complicate personnel turnover. The Quebec, North Shore, and Labrador Railway is a 418-kilometer stretch of track that operates privately for the Iron Ore Company of Canada to transport ore from the mine in Labrador City to the port in Sept-Îles, Quebec. Located north of Sept-Îles, the Gagnon Sud area contains a subsection which experiences relatively high rockfall activity and was chosen for in-depth analysis. This subsection of track runs adjacent to the Moisey River, which presents an added concern in the case of train derailment. The bedrock geology in the track area is almost exclusively quartz paradise. 2 episodes of regional faulting have occurred in the area, the first related to the compression during the Grenville orogeny, and the second due to subsequent extensional rifting, which formed the St. Lawrence lowlands. Slopes in the area range from massive to blocky with an average GSI of 75 and are typically adjacent to the track. Several streams and rivers pass through the rock mass, which can freeze during the winter months and create large ice mounds like the ones shown in photo B. Following a train operator fatality due to a rockfall-related derailment, the IOC sought to develop a life loss risk assessment methodology that could be used to inform future hazard-related engineering decisions. The result was the IOC Geohazard Management System, which was implemented in 2015 and uses a risk-based framework to determine slope rating. The specific scenario of interest to the QNSNL Railway is the probability of a rockfall event creating impassable track, leading to a train derailment and a fatality, termed the risk scenario. The risk is estimated as the product of the hazard, defined as the likelihood of the event occurring, and the consequence, defined as the impact of the event should it occur. Estimation of these parameters is done using a variety of metrics, relying on field inspections, engineering judgment, and established literature on the subject. Witnessing a rockfall event is a rare occurrence. Most often, the instance of a rockfall is known to the railway after it has happened by observing visual cues such as debris near the track area, damage to infrastructure, or fresh exposed surfaces on the slope. Keeping this in mind, track personnel remain vigilant in order to report rockfalls in a timely fashion, but they must also compete with harsh weather conditions, such as intense snowfall, which can conceal debris until spring thaw occurs. For this reason, logging the timing of a rockfall is a challenge for railways, but infrastructure like the tripwire fence installed at Herod Bay can support this work. Now let's briefly look at some of the data for the 2 sites. The graphs show the monthly distribution of rockfall events, and a note that they start with August on the left and go to July on the right. Both sites follow a similar trend. Starting on the left, in the fall, both sites experience a relative increase of events in November, followed by a dip in the winter months. We then see a large spike in activity in the springtime, which is followed by a fairly consistent number of rockfalls over the summer months. So let's talk about the methodology. The goal of this analysis was to better understand rockfall mechanisms by quantifying the relationship between weather trends and rockfall events. To do this, an existing methodology developed by previous researchers, many of them from the University of Alberta, that uses von Mises distributions was selected. The methodology has 3 steps. First, the collection of rockfall and nearby weather records. Second, the modeling of monthly weather trends using von Mises distributions. And third, the mixing of von Mises distributions to model the trend shown in the rockfall record. So there are 3 main types of data used for this analysis. The first type of data are the physically measured weather parameters, the daily max and min temperatures, and the amount of precipitation. The second are calculated weather parameters, which for this analysis is the occurrence of a daily freeze-thaw cycle. And finally, the date on which a rockfall event is logged by the railways. Using these records, the modeling of the data can begin. Moving on to step 2, a key part of this methodology is using a circular von Mises distribution to model the weather data trends. The von Mises distribution is a unimodal and symmetrical circular function, meaning it has a range from 0 to 360. But for our purposes, it can be really be thought of as a density function. The two key parameters for the von Mises distribution are mu, which represents the direction of mean frequency, and kappa, which represents how concentrated the data is. The example on the right is an unwrapped representation of this circular von Mises distribution function with a constant mu of 180 degrees at a varying kappa value. Often this technique is used to determine trends in cyclical time series or directional data, such as structural bedding or paleocurrents. However, in this case, we're looking to model seasonal weather trends. Again, the graph on the right starts in August and shows the observed precipitation record for Heron Bay. The blue curve represents the fitted von Mises distribution model. The location of the mu value is shown with the dashed line, meaning the model estimates peak precipitation at Heron Bay occurs in late August, early September. As expected, the model is not perfect, and some gaps to the observed data record can be seen in months like April and June. While von Mises distributions are unimodal and symmetrical, they can be combined with different weightings to form complex, multimodal, and asymmetrical distributions. This was done using the models for the precipitation, freeze-thaw, and wind data. At this step, we're looking to find the best weightings of our weather models and try and replicate the weather trends that we're seeing in the Rockfall record. The plot on the right shows the 4 different models used to match the Heron Bay Rockfall record, with the combined fit shown in the thick gold line. Looking at the results of the modeling, we can see that the methodology shows promise. Gagnon Sud had a slightly lower correlation coefficient of 0.86, while Heron Bay had a correlation of 0.92, and is believed to be the result of using a brief weather and rockfall record at the site. Both models still behave quite similarly, showing a large spike in activity during the spring and a dip in the winter months. However, there are some differences. Gagnon Sud seems to better capture the local rockfall maximum in the fall, while Heron Bay does a relatively better job capturing the consistent rockfall activity over the summer months. The highest weighting of the Gagnon Sud was spring precipitation at 79%, while Heron Bay was annual precipitation at 60%. So looking at the weather records themselves, both sites experience similar annual weather conditions. Gagnon Sud has more precipitation and more extremes, but Heron Bay has been collecting data for much longer, meaning the trends are more well known. There's also the fact that the Coldwell slide fence helps to capture the occurrence of rockfall events, and the track subsection is shorter. So thinking of some of the conclusions for this work, I think it highlights the importance of consistent and quality data collection when conducting any sort of rockfall analyses. The methodology, originally applied to more moderate climate in BC, also appears to work well with the extreme temperatures seen in eastern Canada. In the fall and spring appear to be the 2 primary rockfall seasons, in the fall due to precipitation and the spring due to freeze-thaw, with the significance of the spring events depending on minimum temperatures at the location. Summer rockfalls appear to be caused by storm conditions, typically precipitation events, and the low frequency of events in the winter appears to be the result of ice formation on the rock masses. So thinking of future work from this research, I think there's a lot of opportunity to expand the analysis framework to consider the geotechnical domains, the rock mass parameters where these rockfalls are occurring, looking at the magnitude of rockfall events, and integrating new annual data sets into our analysis. We could also look at new data collection methods and expanding the analysis from the year scale to looking at multi-year climatic trends to understand those long-term cycles better. There could also be further testing done to the sensitivity of the input data, as well as testing on more geohazards and more sites to see how the methodology holds up. We could also consider designing seasonal operational TARP thresholds, which would help guide decisions based on the climatic conditions at the time of year. So I'd like to acknowledge and thank many people for helping me complete this work, Dr. Jean Hutchison and Dr. Dave Gauthier, as well as many members of the RGHRP team. Thank you to Danny Wong and Maywish Raman from CP, as well as Dominique Sirois from the IOC, and Dave Wood, who helped compile this analysis and understand all the data. These are some of the key references. So my apologies, I cannot answer questions virtually today. I'm in the field, but please feel free to reach out over email if you have any questions. I would love to continue these discussions and hear any input that anyone might have. So thank you very much.